Okay, this is AQA, AS Physics, paper 2 from 2021. Practical skills and multiple choice. As per usual, afraid I can't show the paper on screen because otherwise AQA will get the whole channel deleted like they nearly did in the past. But links to the paper and mark scheme are in the description. If you find this helpful, please leave a like, and if you want to help me keep going making these videos, then consider tipping me with the super thanks button. Question 1, we have this micrometer that's being moved between a transmitter and this reflector, and this looks like we're talking about stationary waves. Okay, so we have this graph, and well, first things first, we're being asked to draw a line of best fit, aren't we? So we have current there and we have distance here, and of course it's just going to be a nice curve that looks like that. So what are we being asked? State a value for the position of P. We're told we want the minimum current, so it is going to be right at the bottom there. It might be that point in the middle, it might not be, it probably isn't going to be if you drew it properly, but whatever, so long as you give value at bottom of curve. We're looking for something like 32.7 centimeters, but there is 0.1 centimeter tolerance either side of that. 1.3, we're told that the absolute uncertainty in identifying any minimum current is 0.2 centimeters. I don't think they worded this very well. Gosh, is this going the same way that paper 1 went? I have nightmares about that paper. He identifies Q as the position of the 8th minimum current from P. Right. Determine a percentage uncertainty in the distance PQ. Oh. Okay, so what they're saying is that there is an uncertainty of 0.2 at both ends, but they really haven't made that clear, which is very much on brand for AQA. So we have plus or minus 0.2 here, plus or minus 0.2 centimeters here as well. So therefore, the absolute uncertainty in PQ is double this, because we have that uncertainty at both ends, because of course we do the distance at Q, take away the distance at P, so it's doubled, isn't it? Uncertainty never goes down apart from when you're square rooting things or similar. We're looking for the percentage uncertainty in PQ. Any percentage uncertainty is the actual or absolute uncertainty divided by the value, and then times it by 100 to turn it into a percentage. So there's going to be 0.4 divided by 50.9 times 100, which is the same as just saying 40 divided by 50.9. So we should end up with an answer that is less than 1%. And we end up with I'm going to call that 0.79%. Well, I think we should round that to 0.8%, and actually that's what they've done in the mark scheme as well. Percentage uncertainty is a bit difficult when we're thinking about sig figs with that, but I guess we could say that the absolute uncertainty is to 1 sig fig, therefore our percentage uncertainty should be as well. 1.4, deduce the frequency of the microwaves produced by T. Well, we know that is going to be something to do with our wave equation, V or C equals F lambda. We know that V is 3 times 10 to the 8 meters per second. So the question is, what is the wavelength? So let's have a look. We can see that P to Q is the 8th minimum. So there's 1, 2, 3, 4, 5, 6, 7, 8. And so we should have a minimum current there. So that means nodes at those points. So we have the 8th harmonic between P and Q. So therefore we can say that this length here is, well, it's not 8 wavelengths, is it? Because we have 1, 2, 3, 4 wavelengths. So 4 lambda. Therefore, lambda is going to be equal to L over 4. So that's our 50.9 centimeters. I tell you what, we should probably turn that into meters. Divided by 4. That gives us, let's be accurate for the time being, meters. So therefore, F is equal to speed over wavelength. So there's 3 times 10 to the 8 divided by wavelength. And that gives us 2.3, we should probably go to 3 sig figs, because this is 3 sig figs. Technically, this is 3 sig figs too. So we're going to say 2.36 times 10 to the 9 hertz. Not a super easy question though, that one, because it's a little bit confusing as to what is actually set up between P and Q. because we're not moving the reflector, that's when we should be thinking in terms of stationary waves. If the reflector is being moved, that's when we think about just path difference instead. That's the sort of rule of thumb. 1.5, oh, we're still going. So it's placed where it is a minimum. And now the detector is turned 90 degrees and it's gone to 0, which means, of course, it's because the microwaves are polarized. We're being asked for the property. So yes, it's polarization, but that can only happen if the waves are polarized to begin with. Question 2, we have this mass. We've seen this question so many times before, I think. So we have this mass hanging down. So we're being asked when weight is 1 Newton, y is equal to 6.34 centimeters. So we're looking for the extension. So we have this, that, and the mass hanging down. This is our y, and we're looking for the extension in the actual wire itself. So I guess actually we should be treating it as 2 separate wires and then adding it up. So we should be looking for the extension in both. So the first bit is easy. We just have to treat it as a triangle. So we say that this here is 6.34 centimeters. This here is 1.5 meters. So I guess we should turn this into meters divided by 100. So therefore we're just looking for the hypotenuse. So we know h is going to be equal to square root of 1.5 squared plus 0.0634 squared. That gives us 1.501, let's go for 3 meters. Therefore, extension in 1/2 is just going to be this take away 1.5, so it's just going to be 0.0013 or 1.3 millimeters. So therefore, total extension is going to be double that, so 2.6 millimeters. But yeah, it might be a bit difficult. You might not have thought about splitting it into 2 separate wires, but that's the best way to go about this. We're being asked for the tension in the wires. I say the wires, yes, we can treat them as separate wires, so it doesn't matter. 2 ways that we can do this. We can think about the forces just adding up to 0, and my arrows should really be the other way here. So tension there, and then we have the weight pulling down. So we can think of it as weight pulling down and then balancing these 2 forces here, and so therefore we can make a triangle from these because they are in equilibrium. Weight going down and then 1 tension going there, 1 tension going back up there. Because we are going to have to think about an angle, so let's think about it from the horizontal here. So again, that's theta there too. So if that's the case, that means that this here is 2 theta, and so therefore we can just split it in half. We have a right angle triangle, so therefore we can just say, well, we're looking for, if we just take 1/2, this is 0.5 newtons, this is 0.5 newtons, we're just looking for the tension in here. So in order to find out this angle, we need to use trig and our distances from earlier. So this was 1.5 meters. This was, what was it, 6.34, so 0.0634 meters. Therefore, theta is going to be equal to the inverse tan, opposite over hypotenuse. So that gives us an angle of 2.42 degrees. Let's be accurate to begin with. So therefore, going back to our forces here, we can say that we have this time the opposite and the hypotenuse. So we can say that sine theta is equal to opposite over hypotenuse. So therefore, sine of 2.42 degrees is equal to 0.5 divided by our unknown tension. So therefore, tension is going to be equal to half of sine of 2.42 degrees. And so just swapping these 2 around, we end up with the tension being equal to 0.5 over sine of 2.42. And we end up with, let's go to 3 sig figs, why not? So 11.8 newtons. That is not an easy question. There is the alternative way of doing it, where you equate the sideways forces and vertical forces, and then you have two simultaneous equations. But this is probably the easier way. Make yourself a forces triangle, because we know they're in equilibrium, and then you can just use half the weight as one of your sides. Now, of course, you can use this triangle shortcut because the angles of the wires are the same, but if you had different angles, then it is probably better to use your simultaneous equations method instead. So well done if you got that right. 2.3, okay, we have here this beastie equation. The ratio of weight to the sagging is equal to that over, what's that, x cubed? Plus some constant. So of course this is going to be a straight line graph, isn't it? Okay, so that's good. We have w over y there. That's good. Don't get confused. This is our y equals mx plus c. It's going to be. Don't get confused though, because they've used y and x. We have a straight line graph, so we're probably going to have to find out the, we're trying to find out the Young modulus. So what do we have on the x-axis? It's y squared. So therefore y squared is our x. So that means EA spores over x cubed is our gradient. So gradient is equal to EA over x cubed. We're looking for the Young modulus, so therefore rearranging this, E is going to be equal to the gradient times x cubed divided by our cross-sectional area. So what are we going to say our gradient is? Draw yourself a line of best fit. Make sure that you use a big old triangle, not a small triangle. I'm going to have a gradient of about 3,850. Times that by, what was x? 1.5 cubed divided by the cross-sectional area of 1.11 times 10 to the minus 7. And that gives us a fairly normal order of magnitude for a Young modulus. I'm going to say 1.17 times 10 to the 11, and the unit of course is pascals. 2.4, determine the dimensional units for K. That's how we say that, the dimensions of K. Well, it is a value on the y-axis, so therefore it's going to be true when all of this is 0. So therefore it's just going to have the same units as what's over here for our y value. So it's going to be the same as the units of weight divided by distance, and so that's just going to be newtons, and then distance of course is just per meters. However, we're not just being asked for SI units, we're being asked for fundamental base units, and we know that newtons is not a base unit. So we know that force is equal to mass times acceleration, and so the dimensions of this is kilograms meters per second squared. So therefore we're going to do newtons, which is the same as kilogram meters per second squared, times by meters to the minus 1. So meters actually cancel out, and we just end up with kilograms per second squared. Question 3, reading a micrometer. State the reading on the micrometer. Okay, so we can see that we're going 0, 1, 2, 3, 4, 5. We have the half millimeters in between as well, but we're going past 5 mil, and we can see 1, 2, 3, 4, but then we can actually see the 4.5 one, but we can't see the 10 mil there, so it's not quite making it to 10 millimeters. So therefore it's going to be 9.5 millimeters plus then the extra bit on our 100th scale, and we can see that it's the 15 that is lined up with there, and this is hundredths of millimeters, so therefore that's going to be 0.15 millimeters. So therefore altogether we end up with 9.65 millimeters. So all we do is get the nearest half a millimeter with our main scale, and then get the hundredths on top of that with the smaller scale, the micrometer scale. 3.2, micrometer has a 0 error. Describe how to determine an accurate measurement for the diameter of a pencil using this micrometer. Well, we close jaws of micrometer using ratchet on the end. So it clicks, and so you're not forcing it, you're not compressing the jaws. Determine zero error. Actual diameter is equal to measured diameter, take away zero error value. Of course, if it ends up being a minus, because it goes past zero, then therefore it's going to be minus, so we're actually adding on that even if we do a minus, so it works. That would actually get you the 2 marks. However, I'm surprised this isn't a 3-mark question. Whenever it comes to measuring the diameter of something, we always measure in multiple places. I guess you should say a long pencil and calculate mean average, because there's not really any other type of average. All right, we have this block at rest. It's on a slope like that, and we have an angle of 23 degrees. And we have, it's on a belt, isn't it? A conveyor belt. So the belt exerts a frictional force on the block when the block is at rest. So let's label this. We know that pulling down here, we have mg sine theta. That is always the case, so mg sine 23. So therefore we must have a frictional force that is equal to that pulling back up the belt. Oh, okay, we're just being asked to calculate that. Cool. So therefore we can say that frictional force is equal to mg sine theta. So that's equal to, what's the mass? 19 kilograms times 9.8. Yeah, 2 sig figs, because the 19 is 2 sig figs, times sine of 23. And that gives us 72.8 newtons. So let's just call that 73 newtons. Whoops, I guess we answered 4.1 and 4.2 there at the same time. 4.3, belt is driven by a motor. The belt and block accelerate uniformly from rest to speed of blah, 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 blah. Okay, calculate the magnitude of the frictional force on the belt on the block during this acceleration. Okay, interesting. So obviously, in this case now, it is the friction that is causing it to accelerate, isn't it? And so it's a little bit cheeky the way they've worded this, but we know we have mg sine theta pulling up there. But if it's going upwards, then we know that the friction must now be greater than that. So we know that F equals ma. A simple equation, but in these kind of questions, it gets fairly complicated because this is the resultant force, this is the total mass, and this is the acceleration. What is the resultant force in this case? Well, it's the frictional force take away mg sine theta. So the friction has to be greater than the force of gravity putting it down the ramp in order to accelerate it upwards. And then that's equal to ma. So we saw that mg sine theta was 73 newtons. We just had that from earlier. And so then that's equal to 19 kilograms times acceleration. Now, what is the acceleration? Well, we know acceleration is change of speed divided by time. So we know it goes from rest, so 0.32 divided by 0.5. So it's just going to be double that. So it's going to be 0.64 meters per second squared. So there we go. Times that by 0.64 meters squared. So basically, in order to get the frictional force, we just add on the 73 onto the end there. And so we end up with 85 newtons. 4.4, we have a voltage of 110 volts, no internal resistance, and we have the current being 5 amps. We have the efficiency is 28%, and the belt travels at 0.32 meters per second. That is 8 meters long. Whew, okay. Ooh, determine the maximum number of blocks that could be moved on the belt at one time. Yowzers. Right, I think this looks like a power situation. So let's find out the power of the motor. So power is equal to IV, so that's going to be 110 times 5, so that's just going to give us 550. However, it's only 28% efficient, so we're going to times that by 0.28, and that gives us 154 watts. Okay, so we have the power of the motor. We know that the force to get these things up there, we saw was 85 newtons. But I've made a mistake. It isn't 85 newtons, is it? Because it's going at a constant speed. And so if it's a constant speed, then the friction is going to be equal to that mg sine theta. And that was just equal to 73 newtons. I knew I'd made a mistake somewhere. Cool. So the power needed for one block is equal to 73 newtons times the speed of 0.32 meters per second. Because once they're up to that speed, then the friction doesn't need to be as great as it did before when it was accelerating it. So that gives us 23 watts. So we can say total number of blocks we can pull up is going to be equal to the total power available divided by the power per block that's needed. I'm making my own units up here, so we end up with the number of blocks on top. And that gives us 6.7 blocks. And so, of course, we can't have that 7th block, so the maximum is just going to be 6 blocks. 5.1, we're talking about an LED. We have a wavelength of, well, let's go with 4.4 times 10 to the minus 7 meters, turn it into meters. We have the rate of photon emission is, okay, so we're going to say photons per second is 3.0 times 10 to the 16. I'm going to write down photons per second here, just like question 4 there. It's useful to come up with your own units because it'll make it easier to figure out what you've got to divide or times in the end. We have a power, we're being asked to find the power. Fine, so we know the energy of each photon is going to be equal to HF, and so that's going to be, well, hc over lambda if we have the wavelength instead. So Planck's constant times by speed of light divided by, we end up adding 7 on top, so that ends up being 15, and then we have minus 34 plus 15, and so that gives us, getting rid of that, we just end up with minus 19. So 6.63 times 10 to the minus 19 times 3 divided by 4.4. You don't have to take that shortcut if you don't want to. And we end up with an energy of 4.5 times 10 to the minus 19 joules per photon. So we have photons per second, joules per photon. If we're looking for power, then we're looking for joules per second. So therefore we're going to do 4.5 times 10 to the minus 19 joules per photon. I'm just going to put that there, times that by 3 times 10 to the 16 photons per second. Those cancel and we just end up with joules per second. So therefore, again, powers of 10 minus 19 times 16, so this just ends up being times 10 to the minus 3. I think I can do this in my head, so this ends up being 13.5 times 10 to the minus 3 watts. Or in other words, yeah, there we go, 0.0135 watts. 5.2, we have a graph. It's going up like this, but then we have a straight line there. It starts going straight about there, doesn't it? So we have photons per second here. I'll tell you what, I'm going to say photons per second. That's a nice way of putting it. And we have current in milliamps. Student claims that the red LED... Oh, okay, so hang on a minute. What did we have earlier on? Okay, we had blue light at 440 nanometers, and we have red light at 660 nanometers. So figure 12 shows how the rate of photon emission varies with current up to the maximum operating current. Student claims that the red LED can have twice the power output of the blue LED. Okay, so the blue LED was, what was it? 0.0135 watts. So we want to find out what the power is for the red one. So I guess we can just go for the maximum rate of photon emission. I tell you what, we're just going to go straight for power is equal to hc over lambda, which is the energy for one photon, times that by the photon emission, or the photon emission rate. 6.63 times 10 to the minus 34. That is the speed of light divided by wavelength, this time is 6.6. times 10 to the minus 7 meters, and then times that by what is the maximum photon emission rate. Looks like it is 6.9 times 10 to the 16 photons per second. Let's tidy up some powers to 10 again, so that was 15, so that ended up being minus 19. Then we have, oh yeah, it ended up being minus 3, didn't it? Of course. So that's just 6.63 times 3 times 6.9 times 10 to the minus 3. I'm just sticking the times 10 to the minus 3 on the end there, divided by 6.6. What does this end up being? 0.021 watts. And so therefore, this, doubling this, is equal to 0.027 watts. So no, not possible. 5.3. Student has paint that fluoresces when light of any wavelength is incident on it. She coats the blue LED and the red LED with the paint. Compare the wavelengths of light emitted by the paint on each LED. In your answer, oh gosh, this is a bit complicated, right? So it's all to do with energy levels, isn't it? So, of course, what happens is that photons produced by both LEDs are absorbed by electrons in coating. These emit photons of, well, they will be varying wavelength due to different energy levels. So the thing is that in both cases, we have a photon going in and then it's exciting the electron in the coating up to a level there, but then it's going to come back down various ways. But the point is that it cannot emit photons with an energy greater than the energy of the photon that went in. So photons emitted by coating cannot have energy greater than that of original photon or incident photon, but can have less energy, and therefore longer wavelengths can be emitted. Okay, multiple choice, my favourite. Question 6. What's the specific charge of an oxygen atom as that's gained 2 electrons? Well, the charge, of course, is just going to be 2 lots of 1.6 times 10 to the minus 19 coulombs, that is. And the mass is going to be, well, 15 times the mass of a nucleon. We know they're slightly different, or at least you will do next year in year 13. So specific charge is charge divided by mass. You know what, can we just cancel those because I think they're so similar and the answers are so different. So plus 27, so this ends up being just times 10 to the 8. You say 2 times 10 to the 8 divided by 15, or in other words, 2 times 10 to the 7 divided by 1.5. And well, I think that's going to give us then 1.3 times 10 to the 7. So I think that's our answer. Sure enough, it is. Of course, it's going to be a minus, isn't it? Well, the answer is A. 7, what's the exchange particle for the weak interaction? Easy, it's W plus. Pion is for strong, photon is for EM. Lepton, well, leptons are particles that do interact through the weak interaction. It's not an exchange particle. 8, baryon has a quark structure DSS and decays by the weak interaction. What are the possible decays of this baryon? Quark structure of a lambda 0 is UDS. So let's check A. So we have DSS going to UDS plus, well, it's a pi minus, so therefore it's going to be anti-up down to get us to -1. Baryon number 1 goes to 1 plus 0. Yes, that checks out. Charge is -1 goes to 0 -1, so that checks out as well. Leptons, no leptons. So yeah, I think this one is possible. So I think the answer is A. Sure enough, it is. Let's just check B. B, why can't it be a neutron plus pi 0? So baryon number is conserved. Charge is conserved. Why can't it be B? Strangeness isn't conserved, but that's okay because we're told that it's a weak interaction. No leptons either. So why can't it be B? Can't be C because we have a lepton involved. There's no lepton going in. Lepton number isn't conserved. D, well, that's going to be to do with charge, isn't it? We have plus and 0 coming out and we need -1 charge coming out altogether. I figured it out, of course. Because we have strangeness of -2 here and we have a strangeness of 0 here, that's not possible. Because strangeness in weak interactions can only change by 1 or 0. It can't change by 2 or more. That's a really jerky question to put in there. Number 9, muon and anti-muon annihilate. What's the maximum wavelength of the photons? Well, if the particles go in, then what we can do is just forget about half of it. So we can just say that E equals mc squared for the muon, one of the muons is equal to HF, which of course is equal to hc over lambda. Now you're not actually given the mass of a muon, you're just given the rest energy in mega electron volts. So we can say that the energy of the muon is equal to hc over lambda. We're looking for lambda, so just swapping these two around, we can see that lambda is equal to hc over the energy of that muon. I'm just going to call it E. So that's equal to 6.63 times 10 to the minus 34, Planck's constant, times 3 times 10 to the 8, we've done this before, divided by, well, we can see that the rest energy of a muon is, I'm just going to say 106 mega electron volts, times by 1.6 times 10 to the minus 13 if it's mega electron volts. Can I tidy up powers of 10? Probably, so let's go with minus 13, add that onto the top to 8, so we end up with 21, and so then minus 34 plus 21 gives us minus 13, and that gives us 1.17 times 10 to the minus 14 meters, and so it looks like the answer is going to be B. 10, electron has speed, electron's kinetic energy is doubled. What's the new speed of the electron? Well, we know that E is equal to half mv squared, so therefore we're looking for how v changes. We know that E is proportional to v squared, so that means that v is proportional to square root of E. So if the kinetic energy is doubling, that means that v goes up by root 2. So that means that the answer is B. 11. Object of mass is accelerated by constant force F. What's the work done on the object during the acceleration? Trick question. We know that work done is going to be equal to the KE gained by the particle, and so it's just going to be equal to half mv squared. So the answer is D. What a weird question. 12. Which road describes the strong nuclear force? So we know the graph looks like this, and the range is about 3 to 4 femtometers, and it changes from being attracted to repulsive at about half a femtometer. It is repulsive here and it is attractive here. So at 0.25 femtometers it should be repulsive because it's of course below that 0.5. At 2 femtometers it should be attractive, that's about here, maybe slightly to the right, but whatever. 8 femtometers it's negligible because it's all the way over here and the range does not extend that far. So it looks like the answer is going to be D. 13, we have some energy levels. 1, 2, 3. We're going down. That's fine because we only care about the difference in energies, don't we? So we have here 0, minus 2.9 times 10 to the minus 19 and minus 8.6. So what are we being asked? So we have a KE available of 6 times 10 to the minus 19 joules. Okay. That's 2.9, isn't it? And so basically, can it get all the way to here? Well, in order to get all the way there, we can get up to a maximum of minus 2.6. So yes, it could get up here in theory, but of course it can't. So it can get up there, it can't get up there. Oh, okay. We're just being asked what's the kinetic energy of the electron after the collision. Well, this difference in energy here is 8.6, take away 2.9. So that gives us 5.7 times 10 to the minus 19 joules. Therefore, KE left is going to be 6, take away 5.7. And so that's going to give us 0.3. And of course, that's times 10 to the minus 19 joules, isn't it? Or 3 times 10 to the minus 20. So the answer looks like it's going to be A. What are the products when a free neutron decays? Of course, it decays into a proton. It decays into electron as well because we need the charge to balance out, and for lepton number to add up to 0 altogether, lepton number of an electron is +1, so we need an anti-electron neutrino. This of course is beta decay. So the answer is C. Question 15, we have this wave and we have a point X that's at equilibrium. We're told that the frequency is 5 Hertz, wavelength is 1 meter, amplitude is 0.2 meters, and we're looking for where is X going to be 0.15 seconds later. Well, let's find out what the time period is. We know time period is equal to 1 divided by frequency, so that's 1 divided by 5, so that's just 0.2 seconds. So If the time period is 0.2 seconds, but the time itself is 0.15, that means that we have 0.75 or 3/4 of a whole wave or a full time period. But where's the particle going to be? Well, if the wave is going to the right, that means that in a fraction of a second's time, x is going to be going down, then it's going to be going back up, and then if it was a full wave, it would come back down to equilibrium, but that's not happening, so therefore it's just going to be at the top. So it's not going to be C or D because, well, x isn't moving left or right, is it? But it is going to be above mn, so that means the answer is B. 16, what is true for an inelastic collision? Well, that's easy, isn't it? We know that it's only momentum that's conserved. Momentum is always conserved, but kinetic energy is not conserved, so therefore the answer is D. 17, we have this wave again. We're told that we have the first harmonic, but then we're looking for the next harmonic where they're in phase again. Well, let's draw the second harmonic on there. And well, at this point, well, on the first harmonic, P and Q are going to be on the same side of equilibrium, so they're going to be in phase. Remember that particles on a stationary wave, they're either completely in phase or completely in antiphase or out of phase. For the second harmonic, well, they're going to be opposite sides, aren't they? So it can't be that. So it's not going to be A. Let's have a look at the third harmonic. Yes, they are going to be on the first and third loops there. So therefore they are going to be in phase. The answer is B. 18, we have light that is being refracted out of a block. So there's our normal. There's the light ray and it's getting refracted more. There's 30 degrees there. What are we being asked? What's the angle of incidence of the ray at the right-hand boundary? Oh, okay, so it's partially reflecting here, and then it's going to be going into there. Now, there's our normal for the right-hand boundary. So first things first, let's find out this angle here. Let's call this θ1. Let's get Snell's law, n1 sine θ1. n1 sine θ1 equals n2 sine θ2. We're told that it's 1.48 times this sine θ1 is equal to, well, just 1 because it's going into air, times sine of 30. Sine of 30 you should know is half, so actually it's just 0.5. And so just rearranging this, doing inverse sine, and that gives us basically, let's call that 20 degrees. Fine. So that's 20 degrees there. So if that's 20 degrees there, then this by definition also has to be 20 degrees, but that's not our angle of incidence going in, it's this angle here, so that's going to be 70 degrees. So the answer is D. 19, Young's double slit, monochromatic light, blah, 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 blah. So let's get our equation. W is equal to lambda D over S. What causes a decrease in the fringe separation? Okay. So let's go for A first. So decreasing the separation. Nope, that's not going to have the effect because it's going to be the opposite. Increasing the big distance. Nope, that's going to have the opposite effect. C, using monochromatic light of higher frequency. Okay, so if frequency goes up, that means that wavelength goes down. So if wavelength goes down, then therefore W does too. So that has to be our right answer. 20, we have an EMF of 12 volts, classic voltage, and when the resistance of the variable resistor is 10 ohms, the voltmeter reads 10 volts and the ammeter reads 1 amp. Resistance of the variable resistor is changed to 5 ohms. What's the new reading on the ammeter? Let's do it the long way around. So we have IR plus IR. Putting my numbers in, let's put in numbers in first. So just 1 times 10, so that's just going to be 10 plus again 1 times R, so it's just that. So therefore R is going to be 12, take away 10, so that gives us 2 ohms. 2 ohms. So now we're changing it to 5 ohms, so we're going to say E is equal to IR plus R, so therefore the current is going to be equal to just EMF divided by total resistance. It's just V equals IR effectively. So it's just going to be 12 divided by, what's that, 5 plus 2, so 12 divided by 7. And that gives us 1.7 amps. So the answer is B. 21, we have EK max for photoelectric effect. Boop, 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 boop. And that's frequency, that is EK max. We have here Q and we have P. What are we being asked? Which graph shows what it would be for a metal with a greater work function? Greater work function means that it's harder to get electrons out to begin with, more energy is lost getting it out, so it's just going to be shifted down. So therefore our answer looks like it's going to be C. 22 we have, looks like, oh, where's the center of mass? Interesting, okay. Center of mass of the system is at Q. Where is Q going to be? So we have here 3 kilograms and 4 kilograms. Of course, the center of mass is going to be closer to the 4 than it is to the 3. So it's not going to be A, it's not going to be B. So is it going to be 4L over 7 or 2L over 3? Well, you should know this, that this distance here is going to be 3L over 7, so therefore this is going to be 4L over 7. So the answer is C. Basically, it's just a ratio of the mass compared to the total mass. That's it. 23, we have a speed time graph. Of course, we're looking for the area under the graph. So this is just a trapezium, so it's just going to be 20 plus 10 over 2 times the height of it, which is 15. So in other words, 15 times 15. This here is just going to be half of base times height, so that's just 10 times, what's that, 8? No, 7. So 70, so that's 35. So 15 times 15. Now the issue is that this is velocity, and so we have here plus velocity, and down here we have minus velocity. So therefore, the blue bit, he's actually going backwards, back towards the beginning. So the total displacement is going to be 225, that's 15 times 15 of course. Take away 35, and that gives us 190 meters. So the answer is B. I've got to be honest, I was tempted to just go for 260, adding them up. So you got to be careful with the velocity time graph that goes into the negative territory. 24, suitcase is placed, the scale reads 180 while the lift is moving. Okay, so weight is less. It's not going to be a constant velocity because, well, it's a constant velocity when it's just staying still, isn't it? So it can't be that. So it cannot be A or C. So it's going to be B or D. Well, of course, in order to feel weightless, then the thing that you're on needs to be accelerating downwards. So it's moving down with, oh, that's not one of the options. I was going to say moving down with an increasing velocity, but no. If it's going upwards, but then V is decreasing, then it's decelerating. So your body in the suitcase wants to keep on going. So acceleration is going in that direction. V is going in that direction. So the answer is going to be D. Bit of a weird one to wrap your head around. But you just got to think, at a constant velocity, the suitcase wants to keep going. When is it going to feel slightly lighter? Of course, it's got to be when the lift is decelerating downwards, regardless of whether it's moving downwards or upwards. 25, we have a force time graph. Of course, we're going to find the area under this. I can be sure of it. If I'm wrong, then it's going to be the first time ever. Maybe not the first time ever. What is the speed of the ball immediately after being hit? So the area under the graph is half times the base, which is 5 times 10 to the minus 3, times the height of the triangle, which is 1400. So basically, can I do this in my head? So I'm just going to call that 700. So 700 times 5 times 10 to the minus 3. So actually that's 7 times 10 to the 2 times 5 times 10 to the minus 3. So there's going to be cancelling those out. So that's just going to be minus 1. So 35 times 10 to the minus 1. So in other words, just 3.5. That's our impulse. That's our momentum. And so we know that that's equal to mv. So therefore, velocity is going to be equal to this momentum of 3.5 divided by our mass of 0.044. And that gives us 7980 meters per second. So it looks like the answer is going to be C. Okay, 26. A mass is added to a vertical spring that is initially unextended. The mass is then lowered until it hangs stationary on the spring. The extension of the spring is now delta L. What? I mean, AQA, sort yourselves out. How much energy is transferred from the mass spring system? Oh boy, I do not understand this question. How much energy is transferred from the mass spring system? But it's not transferred from the mass spring system because it's just Ooh, this question, what are they on about? Okay, well, I guess we just go with Hooke's law. F is proportional to delta L, and we know that the energy stored is that. So energy is just going to be half F delta L, and the force is just going to be mg, so it's just going to be half mg delta L. So the answer has to be A, I guess. But why do they need to word it like that? AQA, just stop it with the weird wording of questions. Just ask. You're not testing people's physics ability by asking weird questions. 27, we have this table with masses and diameters of these balls. Each sphere is dropped and accelerates to its terminal speed. Okay, 27, what is it true about the accelerations of the spheres at the instant they're released? Well, initial acceleration, that's just going to be due to the mass, isn't it? When we know acceleration doesn't depend on mass at all, so therefore they should have exactly the same acceleration. So the answer should be C. So that's fairly easy, right? Easy. 28, it's going to be slightly harder than me thinks. What is true about the terminal speeds? Let's check A. Terminal speed of X is greater than that of Y. I'll tell you what, let's just actually get the grid, shall we? So we have X, Y, and Z. We have their masses, 1, 5, 1, diameter, 1, 1, 5. Okay, so we know Y is going to have the greatest terminal velocity because it has the smallest diameter and the biggest mass, whereas Z, on the other hand, has the smallest terminal velocity because, well, it has the biggest diameter and the smallest mass, along with X as well. Okay, so therefore let's look at A. Terminal speed of X is great. No, X isn't going to be greater or smaller, so forget about X. B, no, it's not going to be the same either. C, terminal speed of Y is greater than that of Z. Yes, that's true. We just proved that. D can't be true. 29, we have currents. What is the magnitude of a current at X? So we have 2 amps going down there, 4 amps going up there. We have then 4 amps going up here, 1 amp going in here, and then 3 amps going in there. Oh, okay. So therefore, if we have 3 and 1 going in there and then 4 coming out, then the current in here is going to be 0. So therefore we have 4 going in, 2 going in, so it has to be 6 amps going out there. So the answer has to be D. 30, what's the resistance of this arrangement? So we know that 1 over R total is equal to 1 over R. So we just say 1 over 1 plus 1 over 1 plus 1 over 3. And so that's going to be equal to, well, we can change these into 3 over 3, 3 over 3. So we end up with 7 over 3. So therefore our total is going to be equal to 3/7. So the answer has to be A. Easy peasy. 31, we have a graph for 2 components. Of course, we're going to have a resistor and a lamp here. We don't care though. What is 2 components are connected in parallel with a 12 volt supply. So there's our resistor, our straight line, and then there's probably our lamp. What's the current in the battery? Easy. We just need to go up to 12 volts for both of them. Easy, we just need to go up to 12 volts for both of them. It's right at the end of the graph. So for the resistor, it's going to be 14 milliamps. For the lamp, it's going to be 9 milliamps. So therefore, we should have altogether just 15 milliamps. So altogether, we should just have 23 milliamps, shouldn't we? So the answer has to be D. Nice multiple choice questions, actually. I'm liking these, apart from a couple of oddly worded ones, but generally okay. 32, we have... Okay, we're looking for Young modulus, fine. So we have, okay, so let's get our Young modulus equation, FL over A delta L. So now we've got to be careful here, I guess, because we know, so we have it in terms of density, don't we? Now we know density is equal to length times area. Now we know that density is equal to mass divided by volume, volume being length times area. So therefore, I think we'll have to, well, let's have a look at our equations. None of them have A in, so we need to rearrange this for A, don't we? So A is going to be equal to mass over length times density. Popping this in here, we end up with Young modulus is equal to FL over M over L rho times delta L. This ends up being on top. And so we end up with F rho L squared over M delta L. Please be one of the answers. Yeah, that looks like it's going to be A to me. So in that case, it was just writing down what density was and looking for what was missing in the final equations. What did we have to replace? 33, what's the percentage uncertainty or resistivity? So let's write out our equation. Rho is equal to RL over A. But here we have PD and current, so we're going to have to replace R with V over I from Ohm's law. Therefore, resistivity is equal to VL over AI. And we have area as well, so therefore we're going to have to replace this. I tell you what, can I just go with rho is proportional to VL over AI, so therefore proportional to VL over diameter squared times I, because we know that area is pi d squared over 4. So let's check out all our uncertainties. So for the PD, we have 0.3%. For the length, we have 0.2%. For the diameter, we have 2 times 4%. And then for the current, we have 5%. So therefore, 0.3 plus 0.2 plus, I'm just going to call that 8%, plus 5. And that gives us 13.5%. Is that one of our answers? Yes, it is. The answer is C. Nearly there. 34. Superconductors are easy. Increase the strength of electricity cables. Nonsense. Make light dependent resistors. Nonsense. Produce strong magnetic fields. Yes, they do, because the current is huge, so therefore they produce strong magnetic fields. D. Increase the rate of heat transfer. No, they produce no heat because there's no resistance. Finally, 35. What shows the classification of particles? Well, we know that we have particles that get split into hadrons and leptons, and then we know hadrons are split into baryons and mesons, so it looks like it's going to be A. So there we go. Hope you found that helpful. If you did, like I said, please leave a like. If you fancy tipping me, click the super thanks button. It really helps me keep going making these past paper videos. If you need some help, join the Discord, link in description, some very nice people there, and click on the card if you want to go to the playlist with all of the AS papers on. All the best with your studies. See you next time.